String amplitudes have certain distinctive features such as they contain infinitely many massive higher spin exchanges, have asymptotic fall-offs like Rayleigh behavior in largest fixed but negative t limit, and exponential softness in the fixed angle scattering limit. These features make string amplitudes behave differently as compared to standard quantum field theory amplitudes. Take, for example, 4-point massless scattering in open superstring theory, where the amplitude is given by this form. This has poles at positive integer values of s and t. This amplitude can be given by a single channel expansion which contains poles either in the s channel or in the t channel. Note that the domains of convergence for the two different representations are different from each other. One converges for negative values of s, whereas the other series converges for negative t. In quantum field theory, we encounter expansions which have poles both in s channel and t channel, along with possible contact terms. We would like to ask whether string amplitudes admit such field theory expansions. In our work, we find a series representation for open superstring amplitude, which is manifestly crossing symmetric, has poles both in S1 and S2 channels. Unlike the previous series representations, this one converges for any values of S1 and S2 except the positive integer values. Note the presence of the free parameter lambda, which in general can be complex. For the convergence of the series, we require real part of lambda to be greater than -1. Lambda reflects the fact that in the Lagrangian formulation, we have the freedom of redefining the fields which will change the contactants and cubic interactions. Presence of lambda improves the convergence of the series. Here are a few examples of first few mass levels. This one is the massless pole. These are the contact terms appearing at first and second mass levels. Contact terms depend on lambda. X and y are related to S1 and S2 variables. This series can be obtained using a parametric version of local crossing symmetric dispersion relation. S1 is the discontinuity of the amplitude in the S1 channel. This amplitude on the left is independent of lambda. In fact, choosing different values of lambda, we are able to recover known dispersion relations such as fixed t, fixed s, and fixed u. Using the crossing symmetric dispersion relation, we can write down a generic form of tree-level amplitudes which have infinitely many massive higher spin exchanges. CLNs are the partial waves, and the idea of Bootstrap will be to solve for the partial wave coefficient CLNs by imposing certain constraints. In our work, we use minimization of linear entropy, which is related to the cross-section, as a constraint. For more details, please visit our poster, which is based on these two papers.